Okay. Well, my name's Dan Prevost. I'm with Southern Ag Services. We're based out of Starkville, Mississippi. I work throughout the Mississippi, Arkansas, Louisiana areas, doing a lot of things from R&D, on-farm R&D to irrigation, a lot of things in between. But what I want to talk about today is really, kind of in the context of working towards automated irrigation, how we make practical irrigation decisions, basically based on math. How do we take quantifiable soil, water, plant water use attributes and apply that to an irrigation decision rather than just making it based on a gut feeling. So, some of the things that I want to discuss, kind of four main points here, just kind of the basics of soil water plant interactions. And I want to go ahead there and give some credit to Dr. Billy Kingery with Mississippi State for providing a good bit of background information that I'll present here. Then I also want to move into an overview of some of the sensor technologies and how they can contribute to the decisions that we make, talk about some of the assumptions and shortcomings of these technologies, and then just kind of work through an example with some of the volumetric soil moisture sensors that we use. And the challenge of all this is to do it in about 23 minutes. And so I'm going to provide a pretty high level overview, work through some stuff pretty quick, um, but we'll do the best we can do. So, my brain works a little better when I kind of understand, the context of how things work, why things work, that sort of thing. And so just kind of starting with the basics of soil water. And, up here in the top left, we can kind of see a breakdown of how the average soil should be composed. Whereas we have roughly 50%, minerals, organic matter, and the other 50% of the soil pore space, half being water ideally, and the other half being air. Well, obviously that's ideal conditions, and as we all well know, that's not the case in many situations, as you could see in the top right, where whereas in this top 4 to 5 inches of the soil profile, yes, we may have something similar to those average soil conditions, but once we hit these plow pans, compacted layers, obviously that changes. Um, and we'll get more into this just a little bit, how that works into the infield variability and how that influences the irrigation decisions that we make. But getting into just a little more in depth into soil structure and soil water movement and all that, for me it really helps to think about it in terms of within and between these soil aggregates, where we have macropores, which are roughly the size of a paper clip, as an example, and then micropores, which are within these soil aggregates, which are roughly the size of a human hair. So, interesting sidebar from the soils textbook. If we were talking about infiltration today, there's a pretty drastic difference between infiltration rates between the macropores and the micropores. And so, basically, when you have these micropores, it takes roughly 10,000 micropores to equal the full water flow rate of one macropore. So pretty big difference. And so if we think about that within context of this photograph in the top right, we can really see how soil structure begins to influence water movement, which in turn influences your irrigation decisions. So just a little interesting sidebar to keep in the back of your mind. So moving on to kind of a real world example. Let's take this field, Bolivar County, Mississippi. This is in the Mississippi Delta. And in the top left up here, we have just a soils map, soil survey map. We can see our soil types broken down. And in this particular field ranges from a Pearson silt loam all the way down to some Dowling uh, clays and in a couple of these corners. Um, and so, when we're talking about placing soil moisture sensors, one of the biggest things that we have to make sure of is that we install that sensor in an area that's representative of that entire irrigation set. For example, I wouldn't want to install a sensor over here in this corner of Dowling to represent this entire field. And we know that's pretty common knowledge nowadays. Something that we use, a technology that we use, is just it measures electrical resistivity across the field, and it can give you an estimate of this relative water holding capacity, this RWTC. and it gives it to you in a percentage of that pore space that should be occupied by water. And so this gives us a way to more quantitatively capture the variation within a field. And so, for example, this field, again, ranging from a Pearson silt loam, which that's going to be our lighter soils, these light colored bands, they're running about 19.5% water right here. But you swing all the way to the, some of the dowlings and to some of these forest hills, and we're approaching 30% relative water holding capacity. So pretty big swing, just based on soil type, soil texture, within this field. And I think it's also important to note that, especially in the Mississippi Delta, I mean we've land leveled and moved dirt on about at least 2/3 of the production land, and so it's a lot of times it's hard to follow these old original soil maps for sensor placement. And so the main point here is just be thinking about this infield variability and making sure it's properly addressed when placing sensors. And also, and again, 5 years ago, this information right here may have been new and groundbreaking. Now it's not. These standard practices for placing sensors, you know, place it on the shoulder of the bed, roughly 1 o'clock. Get away from the field edge. Don't place it within a traffic pattern. We know all this now, so that's pretty common practice. But just wanted to mention that as well. So to summarize that, we've got to put these sensors where they accurately represent the irrigation set, or pretty much everything else we talk about is worthless. So let's transition just a little bit and talk about crop water use. You hear the term ET floated around a lot. Well, what exactly is that? What comprises that? And so it's two things. It's evaporation and transpiration, added together. Evaporation being obviously the change of liquid water to water vapor, and then the transpiration being the passage of water vapor through the plant for the purpose of cooling the plant. And so the combination of both is ET, same as crop water use. In a typical situation, the transpiration makes up 70 to 80% of that total value, with evaporation being 20 to 30, unless you're in saturated soil conditions right after a rain. You have surface moisture readily available. This evaporation rate increases, transpiration decreases. That decreases the cooling effect on the plant, and so that's part of the water stress that we see during saturated soil conditions. So let's move a little bit into more into crop water use and how we can measure that and what that really means and how we can relate that to crop production and yield. And so if we think about it, it's just no different than money in a checking account, but in a bank account. We can think about it from a debit and credit standpoint. So from a debit standpoint, primarily again we're looking at this transpiration through leaves, and we're looking at evaporation from the soil surface. Credits being rainfall and irrigation. There's also a couple other that are a little bit less obvious and a little bit less um, influential, so to speak, in relative conditions. But we can have debits. I mean, we can have water leaching below the root zone in sandy soil conditions. But we can also have credits in our heavier clay soils. We very commonly see water rising through capillary movement from lower in the soil profile. But what we get at the end of the day is we get this net change in storage. Um, and so essentially the daily net change of soil water as measured by soil moisture sensors that's essentially that's crop water use. That's a basically an indirect measurement or a direct measurement estimate of ET. All right, so moving on into how much water is actually needed. And as with a lot of things with agriculture, it depends. But we've got some pretty good data supporting how much water a crop needs by where it is in the physiological growth stage. And so, just taking corn and soybeans, for example, we can see how, over here, early vegetative, we may be, a tenth of an inch per day demand, whereas, peak demand right at tassel, we're a little over 3/10 per day in corn. Similar trend in soybeans, very, very slightly less. But this is readily available information that we have. So this is our target. We know that In order for water to not be a yield limiting factor for these crops, this is the amount of water that that crop needs to have on a daily basis. So if we cannot provide that amount of water due to drought or due to soil structure, what is the effect on yield? And so there's some work out of Nebraska here that shows in corn estimates of yield loss per day of water stress. And so, we can see right here in this table, um, or in this graph, where again, right here at peak reproduction, where we're needing over 3/10 of water a day. If we're not meeting that, we can see, 8% yield loss. I mean, that could go anywhere from, 3 to 9 bushels per day of yield loss due to water stress. So at the end of the day, getting the water through this plant, that's what matters. Um, I want to look at that a little bit closer here in just a little bit. So, but first, we want to talk about what it takes to get the water to the plant. And again, this is just kind of going back to the basics a little bit. And where we're going with this is soil water movement, and getting to how that's measured. But specifically, so top left corner, all these macro pores within the soil aggregates, they're full of water. This is our saturation point. We move on down, water starts to drain out to the macro pores. It's primarily held in some micro pores. We get closer to field capacity, and then water keeps on moving out. And so this is really the irrigation um, area that we want to look at. So what we want to discuss is the tension that the soil particles hold this water and the amount of essentially vacuum that is required for that plant to those plant roots to extract this water from the soil. Just another brief reminder on all this. We're very well of how soil texture influences overall soil water content. This is just a graph showing from, sand to clay, how the soil texture influences the total volume of water that the soil can hold, but also what's available. Just because we have more water in a clay soil does not mean that it's available. And that goes back to again, those finer soil particles, smaller aggregates, requiring a higher tension or vacuum to get that water out. And so this gets into the concept of matrix potential and soil water tension. And I'm gonna relay this into a discussion of the watermark aerometer style sensors. This graph is reporting in megapascals, but we can convert that to centibars, where saturation point we're about 0 centibars, field capacity around 30, permanent wilting point around 150, or common irrigation thresholds here in the 70 to 90 to 100 range depending on growth stage. So going into some of the sensors and how we can measure um, the amount of water that is available. This tensiometers, they've been around for a long time, probably pushing 70 years now. And essentially, all this is a ceramic cup where a vacuum is pulled to measure the amount of essentially suction that is required to draw water into the plant through the root. So this is just simulating the root. Pretty straightforward. Um, Practically, for making irrigation decisions, this old tensiometer, it's just not very practical at a field farm, production scale to do. And that's where these watermark sensors come in. These watermark sensors use electrical current. So this sensor is actually measuring electrical resistance, and they have an equation in place that estimates soil water tension based on that electrical current that is measured. And most people nowadays are familiar with the output of these watermark sensors in terms of centibars of pressure needed and the irrigation thresholds involved there. But again, what this tells us is the vacuum required to acquire that water, and at which point those roots can't sufficiently get water. That's when we want to initiate irrigation. This does not tell us about how much water that crop is actually using and whether or not we're meeting that demand. It does indirectly, but not directly. So transitioning just a little bit to another type probe, like a volumetric type probe, where the watermark style sensor is would be one sensor we would place, maybe four of them, then a soil profile at different depths. These Syntec probes, we have sensors every 4 inches that run the full length of the probe, whether it be a 36-inch probe or 48-inch probe. And it actually measures electrical capacitance every 4 inches. And there's an equation that relates that measurement of electrical capacitance to an estimate of the volume of water held in the soil profile. And so when we look at the output from these volumetric probes, we look at it in depth increments, 4 inch increments, from 2 inches to 34 inches here. And so essentially, this blue line, that's a 2 inch sensor. We have 0.9 inches of water represented in that section of the soil profile, so forth and so on, all the way down to where 34 inches we have roughly 2 inches of water. So in this profile right here, we have a total of 15.3 inches of water. That is total water. That does not tell us what is available to that plant. And so with the volumetric sensors, how we look at that, we're looking at actual daily water use. And so if we look at this image in the top left, we zoom in on this stair step type pattern that we see, where essentially during the daytime we're using water, and so our line is trending down. That shows that we are using water. At night, that line flattens out. That evaporation, transpiration is slowing down to a bare minimum, so that line flattens out. So we get this stair stepping pattern. And whenever we start to run out of water, or those not running out of water, but the plant can no longer pull it through those roots, the tension is too high, this line flattens out. And so essentially what we see are flatter lines at or near saturation. We go through stages where we have readily available water, our lines flatten out, we're in a water deficit, we irrigate, or we catch rain, and we start the process over again. But, interesting to point out, this change right here, this stair step, this daily change, that's our actual crop water use. And so that's one of the big advantages of these volumetric type sensors. And so if we look at kind of some of the pros and cons of both, starting with these tension based, water markerometer sensors, they are simple and reliable. They're cheap. They work good, and we have volumes of research that Mississippi State has conducted that have developed irrigation thresholds using these sensors that provides the most optimal, ROI for an irrigation decision. Um, so some of the cons of these is that they don't provide an actual estimate of crop water use, which I'm going to get to towards the end of this presentation. Personally, I think that's a pretty important aspect. We have fewer sensors just because each sensor only represents a specific area, and they're pretty labor intensive for installing. We have less representation of soil water interactions throughout the soil profile. And when we get into irrigation scheduling, forecasting gets a little more difficult. Predicting when, that the weighted sum of those sensors is going to equal, 85 centibars or whatever it may be. There's some difficulties there. So, volumetric type sensors, some of the pros of that is we're looking at an actual estimate of crop water use. So I have the ability not only just to look at it from a irrigation timing perspective, but also from a more agronomic systems type perspective. And I can ask the question, is my crop getting the water that it needs? I can also, because I have sensors every 4 inches throughout that probe, I can actively determine where the active rooting zone is, and I can update my calculations frequently to represent from where my roots are pulling water. As that crop grows, as those roots get deeper, I can update that and just in general be more accurate than I would if I only had three or four, watermark type sensors involved. Um, Cons to those, they are more expensive, and it takes time to establish those initial irrigation triggers. As I showed in this previous slide, if we install one of these sensors, in a field with no history, initially it takes time to figure out where this area of water deficit is, and how long it's going to take us to get there. And that's something I kind of want to address next. Is what is obviously these are some very good tools. Both types of sensors, um, they both have great places on the farm, and a lot of it is going to be what the actual grower prefers to use and what they're trying to achieve out of it. Is it a simple irrigation decision, or is it gaining a better understanding of what's going on beneath the soil surface, making irrigation decisions, and using it to inform the overall picture? So, how can we link those two technologies together? The linkage is something called a soil water characteristic curve, and these curves are these there's a limit eventually in cubic kilopascals, but you can just ignore that and think of this in inches of water versus centibars of pressure. And so what these lines do is allow us to say, okay, if I have X number of inches of water in this soil type, that is the equivalent to X centibars of vacuum required, so to speak, for that plant root to acquire water. And so these are different. These curves are different by soil type. And these curves are different by soil horizon. Texture influences these curves, as does compaction and soil density. So, but this is the potential that we have to link those two type sensors together, and ultimately support overall better decisions. And so, I want to work through an example here just a second, using a volumetric sensor. But the first thing I want to do is just talk through some of the assumptions that we make and some of the shortcomings that are associated with all this. I think it's important, especially again in context of working towards making some automated irrigation decisions, that we understand, the risks involved with that. Not to be, a negative Nancy towards it, so to speak, but to understand, what those risks are, and identify areas for improvement. How can we continually do better, working towards this? And so we're going to assume, working through this next example, that sensors placed right, optimally within the field. It adequately represents average conditions within the irrigation set. We know how many days it takes to make the round in that particular irrigation set. Our soil sensor calibration equations are applicable for that specific soil type and condition. And this is something that's pretty important. And as you're evaluating different sensors, this is, as a producer, a question that you probably need to ask: are the equations, because it's, again, these sensors that are used, they are not directly estimating or measuring. So they're not measuring soil water tension or soil or the volume of soil water. They're estimating them based off some, electrical current and some equations. So, are these equations correct? So are the sensors installed operating correctly? And then also, we're going to assume static atmospheric conditions, or we're going to use an ET forecast. And, that's kind of, we're getting to splitting hairs a little bit, talking about this, but I think it's worth mentioning. So, just some of the shortcomings, and some of these we've already discussed. It can be difficult to place a sensor to where it adequately represents an irrigation set. I mean, we've got a tremendous amount of soil variability in a lot of areas, particularly in the Delta, where we have alluvial soils that are just, layer upon layer of different soils. Um, Practically, we can be in the middle of an irrigation set and catch a rain, and that just interrupts the whole pattern and just makes things complicated. And again, going back to the need for these localized sensor equations and the soil water characteristic curves, the reason that they're, not, I don't want to say they're not abundantly adequate, is they're tough. They require a lot of sweat and time and resources to develop. All right, so let's move into just an example of of the mathematical equation for how we would work through this with a volumetric type sensor. And so, when I pull up my or what I'm looking at, my top graph here, I have my individual sensors listed out uh, by depth. And so I can come in and I can see these little stair step patterns moving throughout, lower and lower in the profile. And so for some scheduling decision on when it may be, and so I definitely see root activity 30-inch depth. So for this exercise, I'm going to call my root zone, from 0 to 30 is 15.3 inches. That's just the sum of total water in this area. So if I get down here, this is what we call a sum of sensors. So I basically take these individual sensor lines here and I add them all together. And this represents my total water use. And so this is where I can go back and look at my individual stair step pattern and how much water I'm moving, using per day. But I can also run out of water, so I know I need to irrigate. So, in this example, we can see the line starting to flatten out right at 12 and a half inches. Now, insert that soil water characteristic curve, and I'm just using this as an example. That soil water characteristic curve may tell me, hey, at 12 inches, you're at 85 centibars for this soil type. This is when you need to consider initiating irrigation. And so what this allows me to do is to, whenever I install this sensor back here on the front end, through using that soil water characteristic curve, I can go ahead and set my irrigation, my refill point based on that curve. So this eliminates the need for me to watch this and wait on it to flatten out to know to make an irrigation decision. So what I do, if I take the root zone water 15.3 inches to my refill point of 12 and a half inches, and if I look at that difference, the difference between the two is 2.8 inches. So I have 2.8 inches of readily available water. And this is going to be the basis for scheduling my next irrigation event, working under the assumptions that we've already discussed. And so I can go back and I can look at my daily water use. And so if I'm just using this graph because it's easier to see than if we were looking at a bunch of numbers on the table. But this calculation is done on actual values that this line represents. And so my average daily water use, for this time period right here is basically 3.5 tenths of water per day. And so if I just break that down to a very simple mathematical equation, 2.8 inches of readily available water divided by 0.35 inches per day of my water use, I have 8 days of available water. I know it takes me, say, just for example, 3 days to make the round on this particular set. So that's pretty straightforward and simple. And we're at a point now where we can make good irrigation decisions with confidence. We've really come a long way in the past 5, 6, 7, 8 years in doing that. The opportunity that I see with these volumetric sensors, it really extends beyond you looking at it from just an irrigation decision perspective. Again, kind of as I started, I want to understand what's happening in that profile in the root zone. What is influencing water use, and how can I determine whether or not I have adequate water use or whether that's a yield limiting factor. And so this example right here, this is two sensors. They are installed in the same field. They are 12 rows apart, but there's a difference in management between the two sides. This top side right here has been minimal tillage, no cover crops for I think at this point in time is about 3 years. Where this bottom field, same minimal tillage regime, but it had cover crops involved. And so if I look at daily water use, my average during this time frame right here, as measured by both sensors, again, this is 12 rows apart, so they're installed correctly. We're not in traffic middles. We have not changed soil types or soil zones, but there's a dramatic difference in the amount of daily water use between these two sides of the field. You can see it in the sensor where we have 0.17 inches here versus 0.35, so almost twice the daily water use on this cover crop side as in the non-cover crop, essentially no till. Um, Huge difference, and you can see this in the crop, man, plain as day. You can see it in subsequent crops as well. You go to this field in the heat of summer in July, and you will see the difference: water stress versus non-water stress. And this is a Dundee silt loam, good soils, furrow irrigated. So we would think if I'm watering every 7 to 10 days, that I'm meeting my plant water needs. When in reality, I'm not. The soil structure, so that's there, the soil profile is not capable of providing adequate water. And so where I believe that leads us to, especially with these volumetric sensors, is it allows us to really look at how management influences soil structure, crop water use, and also irrigation decisions. Um, but for me, it really helps us understand what's going on beneath the soil surface. Things that we can't see. It's really kind of a window to the underground world, and it really, it kind of allows us to ask the question. Is the soil providing what it needs, or are we leaving yield on the table? And are there areas for improvement? So with that, I'm going to wrap up. And if we were doing this in person, I would actually welcome some discussion and questions. But with that, I'll just close. Thank you.
Hello, everyone. I'm Gurbir Singh. I'm a soil scientist and assistant professor at Delta Research and Extension Center located in Stonewall, Mississippi. And thank you, everyone, for giving me this opportunity to talk about my research. The title for my research is Irrigated and Dryland Corn Production Under Striptill and Conventional Tillage. And before going into my presentation, I would like to acknowledge my co-authors, Dr. Gurbir and Dr. Jason Cruz. To begin with, I have an outline, and what I will do is I'll talk about my introduction first. So what was the rationale behind doing this research, and then I'll talk on to my objectives, and then move on to our study design and what kind of data we collected, and finally I move on to some of our preliminary results that are results for our first year, and then I'll eventually move on to our conclusions. So to begin with the introduction, in Mississippi Delta, we have a conventional tillage system, and just to explain what the conventional tillage system looks like, and Mississippi Delta is we have two passes of disking, a pass of a field cultivator, and a pass of a panhipper or a bed roller. So basically, we're looking at 4 to 5 tillage operations per season. And if we are using a panhipper, then we are running a dual before planting in spring. So it adds another field trip, another tillage implement that goes through our fields. Overall, whenever we say talk about conventional tillage is anything which leaves a residue which is less than 15% on the surface is called conventional tillage. And for example, what we do over here is it's a stale seed bed preparation, where we do all the conventional tillage operation if the weather permits in fall, and then wait till spring. And in spring, we go ahead and do a burn down application and go ahead and plant our cash crop. And alternative tillage system to our conventional tillage is the reduced tillage system, or also called conservation tillage. There are numerous definitions of it, but for the sake of this presentation, I'll say that reduced till or conservation tillage is a system of minimum surface disturbance of soil and maximum retention of crop residue on the soil surface. And overall, we have to see that if we keep more than 30% of crop residue on the surface, and we'll call it as a reduced till or a conservation tillage system. An example of that is a strip till. And in this picture, you can see that we have strip till running in the field, and it's just tilling a strip where we'll plant our crop in the next year, and it leaves a residue in between the planted rows. So then moving on to one of most of the critical question is that strip till, no till, reduced tillage practices have been there for a while, and farmers do know about it. But what's the reason that reduced tillage or conservation tillage systems are not adopted in Mississippi Delta at that large scale? First issue is the drainage issue. We have soils that are heavy, and then we have rainfall that is around 54 inches per year. And most of this rain comes during spring before our planting season. And as a result, soil is always saturated and flooded. So, to help with drainage, we need to have some kind of surface drainage, and if we need the surface drainage, then we'll go with building beds, and then furrows to help with drainage of water as soon as possible from our field. Second issue, the major issue that we have over here is the irrigation issue. Uh, uh, what happens during June and July is where temperature reaches quite high, and as a result, we need supplemental irrigation. And the most widely adopted irrigation system in Mississippi Delta is furrow irrigation. And how we can do it? We need to have furrows to do the furrow irrigation. So it comes back that we have to do conventional tillage to build furrows every year, and uh, and then it depends on what kind of soil we have. If we have a heavy clay soil, and if we have a sandy loam soil, then we have to reshape the beds again and again. So moving on to our next question is, can a reduced tillage system be developed or adopted in Mississippi Delta? So yes, it can, but we'll have to solve drainage issue and irrigation issue to have these tillage system be adopted, or a reduced tillage system to be adopted in the Delta region. Drainage issue, we have to take a hybrid approach for that. Some farmers have already been doing it because they have a heavier ground. What they will do is they will go ahead and do the bed preparation on the alternate years, and if they are not able to put their new beds every year, then they will run a middle plow through it to help with the irrigation during the season. Another thing that we can do is, with the help with the drainage, is we can use subsurface tile drainage system, and that's a whole different subject and matter to talk about. And then, what kind of tillage implement we'll need for this? It will be probably a strip tillage system, and if we can add on to it as a precision fertilizer applicator to it, then we can apply fertilizer on the strip on the go with the strip till instrument. So, what is strip till actually? What is strip tillage? So, the strip tillage is defined as less than full width tillage of varying intensity that is conducted parallel to the row direction, and generally no more than one fourth of plow layer is disturbed. But the goal of the strip till is to create a seedbed condition in the road that is similar to that achieved by a regular moldboard pro or regular tilling, and while leaving a relatively high amount of crop residue on the interrow and soil surface to reduce on the interrow soil surface to reduce erosion. So, further, for those who don't know what a strip tillage implement looks like, so this is the image of one of the row unit for the strip till. So it has a parallel linkage, it has a depth band culture, and it has row cleaners to clean and remove trash in front of the rows, especially from the seed beds. And then it can also have a tillage shank that can go and do a deep tillage up to 11 inches, and then it have a baby cultures which can be adjusted for the depth to do deep or shallow tillage, and at the end it has a rolling basket, and rolling basket actually is just like a do-all that we run on pan-head furrows. So three major classifications of strip till are strip tills with just the row cleaning or residue removing units, or strip till with a shallow tillage. So this wavy culture we can move up and down and do a shallow tillage, and then if we want to do a deep tillage, we can do a deep tillage with the shank. And this shank also have the capacity to actually band liquid and as well as dry fertilizer. If we putting any box or some kind of air delivery fertilizer system along with it. So this video just shows that how a strip till system works in the field, and this was just over a couple of trial runs that we were doing, and we were trying to adjust the trash whippers depth and depth at which we want to till and how deep we want to have a shank. Moving on to so why strip till we should do strip till. So first of all, if we want to improve the structure of the soil, then we should go with the strip till. So if we want to save fuel, yes, we should go with the strip till. So in this graph right here, if you see that this is a published research already done. So what they did was they compared disc tillage plus field cultivator to strip till in corn soybean rotation, and then estimated the tillage fuel cost per acre. And the red bars show the fuel cost for the corn, and the gray bars show the fuel cost for soybean. So if we are disking and doing regular tillage operations, then the costs are more than $20.50 per acre every year. And if we are doing strip till, the cost is reduced by at least $6 or maybe $12, depending upon how what crop we have. So if we're doing a banded fertilizer, then it reduces the P and K loss with the strip till. So another advantage of strip till is it warms the till strip sooner in spring to and promote germination and help with plant emergence. And most important thing of the tillage implement is that if we have a subsoiling shank with it, that shank can go up to 11 inches and can help reduce the compaction. And that compaction layer beneath our seed bed is actually broken by that tillage shank. So that is more helpful than what we use. That could be more helpful than our regular subsoiler that we have been using over here. But to to answer all these questions, we have to actually formulate a study in the Mississippi Delta. For that, we established a couple objectives. So the and I'll cover these objectives in this slide, and then I'll move on to the treatment design. So, our overall objective for this study was to quantify the effect of tillage, irrigation, fertilizer placement on corn production. Specific objectives were to quantify the effect of strip tillage, conventional tillage, subsoiling, and fertilizer placement on stand establishment, corn yield, quality, nutrient uptake, and P and K use efficiency, and to evaluate the effects of tillage system with P and K placement under irrigated and non-irrigated conditions on soil water availability, irrigation use efficiency, compaction, soil P and K test value, and also to determine the economic feasibility of strip till for Mississippi corn growers. So our study design was, what we did was, we wanted to see and run this tillage study in two scenarios. One is irrigated and second is dryland corn. So to irrigate corn, we use watermark sensors with a threshold of negative 40 kPa. That is a very wet threshold. Whenever we reach that, then we started irrigating our corn. For dryland, which was purely dryland corn, and then how our treatment structure was, we had three tillage systems. One is conventional tillage. The conventional tillage, as I discussed earlier, it was two disking, one field cultivator, then hand heifer in fall and dual in spring before planting. Then we had subsoiling, where we did subsoiling in fall, and then had conventional till as described in treatment one, and then finally we had a strip till treatment. And with the strip till, we did strip till in fall with the shank that went to 8 inches depth. And under each of the tillage treatment, we had three fertilizer placement treatments, and these treatments were either broadcast of the fertilizer or broadcast incorporated of the fertilizer, or deep band incorporated in the strip with the strip till. And then finally, the last was the control with no controlled fertilizer. So that being said, like we have conventional till. Under conventional till, what we did was we broadcasted the fertilizer after doing conventional tillage. Then similarly, before doing conventional tillage, we broadcasted the fertilizer so that it's incorporated in the soil. And same thing with the subsoiling, we have these two treatments. And then finally with the strip till was, we did the strip till and then broadcasted the P and K after fall tillage. And then, in addition to the strip till incorporated, what we did was we used the shank for the strip till to incorporate our fertilizer underneath the seed bed. I'll cover the treatments again once we go into the results. So overall study design was a split plot design with 4 applications for each treatment. These pictures shows a Gandhi box, that is the air delivery system, and it has these white hoses where we can put a dry fertilizer. And the second picture right here shows the shank that went up to 8 inches deep, and fertilizer was delivered through these white tubes and put at the 8 inches depth right underneath the seed bed. And then it had the baby cultures for doing deep or shallow tillage, and then at the end it had this rolling basket to actually pulverize all the soil and make that seed bed very smooth. So moving on to the data collection, since this is a soil fertility and irrigation project, so we had to do some kind of soil sampling. And what we did was we collected baseline soil samples to see what were the differences, overall differences in the study site. And then at end of the season, we also collected soil samples from 0 to 6 and 6 to 12 inches depth from every treatment, and had it analyzed for residual soil fertility in 2020. And we also collected plant height data on biweekly basis and chlorophyll meter readings on biweekly basis. Um, at at the physiological maturity, what we did was we collected we did the stand count, and we also collected silage yield, and the silage yield was used to estimate silage P and K uptake. Moving on to the harvest data. So at the end of the season, we harvested our plots with the Kincaid two-row plot combine, and we got test weights, moisture, and we also collected grain samples at the time of harvesting and had those grain samples analyzed for grain quality. And grain quality included moisture, oil, and starch. Moving on to our results. So the first results are our corn plant heights, and this picture shows a clear difference that how the corn plant heights were different early in the season. And this figure right here shows the dates on the x-axis and corn height on the y-axis, and corn height goes up to inches from 0 to 120 inches, and there are three treatments listed in this figure. With the gray or black boxes, we have conventional tillage plus incorporated fertilizer. Red is the strip tillage plus deep bending fertilizer, and blue is the subsoiling plus incorporated fertilizer. And you see right here in mid of June, corn height of strip till deep bended fertilizer was higher early in the season compared to other treatments. So this was a significant difference, and the significant difference uh, was uh, uh, was was significant difference over here was actually matched up later in the season by other treatments. But the important thing to note over here is that the crops or plants that had a banded fertilizer beneath the seed bed actually had a higher advantage of a higher chance of getting that fertilizer, or a quicker chance of getting that fertilizer and metabolized into the plant biomass. Moving on to our results for corn silage. So this is just a statistical table, and this table is a probability value and numerical degree of freedom associated with the source of variation in statistical analysis. All models will run at 95% confidence, and source of variation gives our treatments. First, we had irrigation treatments. Irrigation was dry land and irrigated. Then there were tillage systems, pre-tillage systems, conventional tillage, subsoiling plus conventional tillage, and then strip tillage. And then there were three fertilizer placements. Three fertilizer placements were fertilizer broadcasted before tillage, fertilizer broadcasted after tillage and incorporated into soil. And in this, where we had strip till for incorporation, we use the banding with the strip till. And then last was our non-fertilized control. And then the statistical model, we have the interactions for each of these treatments. And in this table, we see plant population. There were no significant differences in plant population for silage yield, silage P uptake, and silage K uptakes. We had some significant differences in our treatments. Moving on to our table, so this table shows the influence of irrigation, tillage, and fertilizer placement treatment on plant population, corn silage yield, and P and K uptake. So over here, means followed by the same letter within a column do not differ significantly at P less than 0.05. And if you see over here, we have irrigation treatments, and then we have tillage treatment, and then we have placement of the fertilizer. Silage yields, if we see when we averaged everything based on irrigation and placement, our tillage treatment, strip till and subsoiling had higher solid yield compared to our conventional till. Similarly, when we average everything based on irrigated dry land and our placement of treatments, the potassium uptake in solid was higher for strip till compared to that of the conventional tillage. Moving on to our next results. So next results are of our yields and the quality. And this is also a p-value or a probability value table that we got from our statistical analysis. All the greens over here are the significant values, and similarly, the source of variation is again our treatments, irrigation treatments, tillage systems, pre-tillage systems, fertilizer placement, our fertilizer placement treatment, and then their interactions. So none of the interaction was significant for yield and yield quality. Moving on to our mean value table. So this table is shows the influence of irrigation, tillage system, and fertilizer placement treatments on grain moisture, test weight, grain yield, phosphorus agronomic efficiency, potassium agronomic efficiency, and grain yield. Again, we have irrigation over dry land and irrigated, tillage system is strip till, subsoil and conventional till, and fertilizer placement is no fertilizer, broadcast, and incorporated. And how we calculate phosphorus or potassium agronomic efficiency, it was the difference between yield from treated plot and the yield from control plot divided by the amount of fertilizer applied, P or K applied. So over here, we see especially yield where we are more interested in when we average everything based on irrigation and fertilizer placement, strip till and subsoiling, they had no significant differences, but they were higher than the conventional tillage system. And then if we move on to our agronomic and agronomic efficiencies for P and K, strip till had significantly higher agronomic efficiency for P and K compared to other two tillage systems when combined when averaged based on irrigation and fertilizer placement treatments. These results, this graph shows the residual soil potassium, and we collected this data in 2020, fall 2020, after harvesting of our corn crop. And over here in this figure, you see on the x-axis we have fertilizer placement, no fertilizer, broadcast, and incorporate. On the y-axis we have soil test potassium. And there are two depths. Green color is from 0 to 6 inches, and red color is from 6 to 12 inches. And if you see over here, our incorporated fertilizer had higher residual soil potassium compared to our all other fertilizer placement treatments. Moving on to our next graph. So this graph represents MELEC 3 extractable soil phosphorus after harvest of corn in 2020. And on the x-axis, we have a tillage system, that is conventional tillage, strip tillage, and subsoiling. And on the y-axis, we have soil test phosphorus. And important thing over here to note is that these colors, gray color is for no fertilizer, red color is for broadcast, and the green color is for incorporated. So over here, green color in strip tillage with the A as a letter over there is showing a significantly higher residual P in soil with strip tillage incorporated compared to subsoiling. So this means that what happens is strip till with deep banding conserve the P in the soil, and it has higher residual P left. And as a result, for next year, we might have, if we keep on putting same rate and keep on banding P at the same rate, what will happen? Will start increasing the residual P in the soil. And as a result, it will create zones of high P right underneath the seed bed and low P in the furrow where we are going to irrigate. So as a result, there will be less loss of P from anticipated less loss of P from the strip healthy planting fertilizer compared to other treatments. So finally moving to our conclusions, plant heights over the growing season was higher under strip tillage deep planting treatment, indicating that fertilizer placement in the rooting zone is beneficial. And silage yield and silage potassium uptake was higher in strip tillage treatment compared to conventional tillage when averaged based on irrigation and placement treatments. Corn yields were higher, 20 to 26 bushels per acre in both subsoiling and strip tillage treatments compared to conventional tillage when combined over the irrigation and fertilizer placement treatments. There were no differences in yield between subsoiling and strip tillage. P and K agronomic efficiency was higher for strip tillage compared to other two tillage systems. Finally, soil test phosphorus at the end of the season was highest for the strip till deep planting for the first year and soil sampling. Continuous application of P and K and deep banding would result in creating zones of high P and K soil fertility underneath the seed bed. With precision planting using RTK on the same seed bed, it is anticipated farmers will benefit from strip tillage, deep banding, tillage practice. Additional data from coming years will help answer economic feasibility of strip tillage and panic fertilizer placement systems and Mississippi for Mississippi farmers. And I would like to acknowledge my team who have helped in conducting this research and all of our office associates as well as summer workers who were involved in this research. I'm very thankful to Mississippi Farm Promotion Board for funding this project and also USD ARS for providing some resources to carry out this research. Thank you.
Very interesting, Gurbir.
Yes. So this is just first year of results. I'm hoping next year we'll see some significant differences if the year permits for more irrigations. So this year we're able to irrigate much.
Yeah, I am probably 90% leaning towards strip tillage just for the few hundred acres of cotton that I have next year. Just dealing with some compaction issues and all that. So I've been trying to learn on it myself. So
yeah, I think if with issue with the strip till is that it will give you a return if you start putting banding fertilizer in.
Right.
And that's the key behind it.
Right. Mm-hmm.
Once you create your zones of high fertility and low fertility, then I think you can just stop putting fertilizer for 3-4 years unless you go beyond that threshold.
Right, I understand.
And that's the true use of RTK that we have.
Mm-hmm.
So
absolutely.